when I'm talking about simulating the universe with computers, so maybe maybe I'm the only theoretician in this meeting. So my topic may not lead to immediate collaboration between us, but please remember, so for possible future collaboration between Japan and Kazakhstan, especially for young people. And let me give you. And then I'm a director of Center for Computational Astrophysics, so where I do simulation using supercomputers. And also within this center, we have four-dimensional digital universe project, where I do visualization of astronomical data, which I will show you soon. Then also I belong to the University of Tokyo Department of Astronomy, where I take students, graduate students. And my main research fields are formation and evolution of planetary systems, and well, all these related subjects. And I like travel, so I'm very happy to come here. So, well, I know, all of you know why we are doing astronomy, but let me tell you, in my words, what are goals of astronomy? So first one, we can say, well, this is the physics-oriented way, but to understand the physical laws that govern the universe, right? That's what we like to understand. And in a different way, so more matter-oriented way, so we can say we like to describe the origin and future of everything. So from the cosmic perspective, so which means in the history of the universe, in evolution of the universe, so which we like to understand in a big picture. So that's why, at least I'm interested in astronomy. So to achieve these goals, so now we have three methods in astronomy. The first one is, of course, most of you are doing the observation. So where we use now telescope. So we study this kind of method since we study sterilization, right? So this is to watch the universe. And at the same time, we also studied theoretical astronomy. So where we think of the physics behind what we observe, right? So and to do that, we use so-called pencil and paper. But today also we use computer, right? So until the middle of the last century, these two are only the ways we do astronomy. But around the end of the last century, we got the third method, that is simulation. So where we use a supercomputer and we do experiments of astrophysical phenomena in a virtual universe realized in a computer. So that's the third way. So today, the trinity of these three methods, proceed the understanding of the universe. So are helping each other. So that's the present-day physics. Astrophysics, I think. And what is simulation astronomy? So I will explain in a bit detail. So this is also called as numerical or computational astronomy or astrophysics. So what is the target? So target is unobserved astrophysical phenomena, which we can't see by telescopes, which we cannot observe. So the principle of simulation astronomy is physical laws. So we use first principles to calculate or to simulate the astrophysical phenomena. So where we numerically solve the equations of the physical laws, like equation of motion and fluid equations, and etc. So numerically we solve the equations, and see what happens. So that's the simulation, okay? And in that sense, we can call a supercomputer as, well, theoretical or numerical telescope, because which, by simulation, supercomputer shows us what, the universe, what evolves. So we, the theoreticians call supercomputers as theoretical telescope. And now let me explain the three major categories of astrophysical simulations today. I mean, the large-scale simulations. The first one is gravitational many-body problems, which I'm mainly working on. So where we are interested in the behavior of many-body systems, so which include the large-scale structure of the universe, galaxies, star clusters, and planetary systems. So I'll show you examples soon. The second one is hydrodynamic simulations. And here we are interested in the behavior of gas, or sometimes plasma, in magnetic hydrodynamical simulations. So with these simulations, we investigate industrial clouds, stars, supernova explosions, and accretion disks around the black hole, or many things. And the third one is radiative transfer, in which we are interested in how the light or energy, or photons or light wave, radio waves travels in the universe, in matter, right? So with this simulation, and this radiative transfer simulations tells you how the object looks like. Right, when you see a telescope, then by telescopes, right? So, and we do radiative transfer simulations for the galactic cloud, industrial clouds, for many things. And today, so these simulations covers almost everything, well, every scale of the universe. For the space, the simulations now we do covers from the dust or planets to the whole universe. And for time, so for example, the supernova explosion, we are interested in the phenomena, the time scale of seconds. And also in the large scale structure of the universe, in those simulations, we simulate for the age of the Project Center for Computational Astrophysics. Let me explain. So the acronym for the center is CFCA. So please remember CFCA for the future collaboration. Okay, CFCA in NAOJ. So the CFCA's goals is to operate of open use supercomputers. So we provide astronomers computational resource. We are not using only by ourselves, but we provide. Our computer system is open. And we like to be the center of excellence of simulation astronomy in Japan, and to do so, we develop hardware and also software for simulations. And also we do visualization of astronomical data. And if you're interested in our projects, please look at these URLs, where you can also find beautiful movies, which I will show you from now on. And this video shows our computer system. So we have a variety of computers. So, and I just introduced only, only a few computer systems. So these are lists of computers, but I don't go into detail. But we have supercomputer, so-called massively parallel supercomputer, and we have special purpose computer, and other supercomputer systems. And the fastest one, our supercomputer, is this one. We call it Atelri. This is a Cray X330 supercomputer series. So Cray is an American supercomputer company. And it has the peak speed performance of 1 petaflops. So which means this can calculate double precision floating point operation 1,000 trillion times per second. 1,000 trillion 10 to the 15 times the calculation per second. And this is still now the fastest supercomputer dedicated for astronomy. And this computer is open. And okay, so from now on, I'd like to show you the state-of-the-art simulations, which is done with our supercomputer systems. The first one is the large-scale structure sorted on this. Okay, so this is the gravitational many-body problem, the formation of large-scale structures. So we have now dark matter particles here. And initially, they're on very small, tiny density fluctuations. But this density fluctuation increases by the self-gravity between dark matter particles. So now you see the initial density fluctuation is only 1 part in 100,000. But it enhances by the gravity like this. And through this process, the clusters of galaxies, or so-called large-scale structure of the universe, is formed. So this is one of the largest scale simulation one of our users done, and he got the Golden Bell Prize for his simulations 2 years ago. So he used about 0.1 billion particles for dark matter here. So you see the cluster of galaxies, and they connect to form the web-like structure. So this is the formation of the large scale structure. So this is an example of the gravitational many-body problem. And this visualization was done with this 42U project. Okay, so next one, the next example is the hybrid of gravitational many-body problem and fluid simulation. So this is about the formation of the galaxy, this galaxy, like our Milky Way galaxy. So first we have a protogalactic gas cloud, and this is along the so-called bottom-up formation scenario. So first from the gas cloud, many star clusters are formed. And then by merging of these star clusters, a large galaxy gets formed. So because initially the gas cloud has some angular momentum, so this angular momentum is conserved through this process. So then that's why the largest object is rotating, right? Because it is rotating by the centrifugal force, this disc-like shape is formed. So the time scale of this simulation is about 5 giga-years. And I'm sorry, so these blue things are gas, and the white dots are stars. And as you see here, so by merging of small star clusters, a spiral structure, a spiral galaxy possible way to form spiral galaxy. So also, I'm working on the spiral structures of the galaxy. So I'm very much interested in its structure. So then, let's move on to the solar system, to the Saturn